So we last time stopped, I think, in between games, like understanding how we can use the another toolbox which is available with us, games. So, so we were discussing, like what will be the different structure of the games program, but for your like hands-on purpose, you can download games. So simply type GAMS, and the very first link is from this particular game site, and you can download the different basically like in downloads games, and then different version. Latest release was 52.5.0, and the demo version is always available. Okay, so you can download that demo version. It has certain limitation, but still we can solve like use it. So, in games, licensing file, it is mentioned here somewhere that it is a demo version. It has certain limitations about the number of variables and the number of constants, and these solvers basically these many number of solvers it support, but with their limited computational features are basically uh, different, like limitation on the variables and constants. So we were discussing like how the game structure looks like, and we discussed about this part. Like these are the various elements in the games programming, and you can see. So very first is sets. So you have to define different sets here. This denomination, like here you can see, like this is the actual syntax how we write the set. So this red part is mandatory. You have to mention a set as a, like, so this is a syntax in the games. Then set name, you can give any name to a particular set. Then a description can be a single word, basically a line. Okay, so comprising of many words. So a description is again a user defined, so you can provide any description here. Then in these, like slash, you provide the index. So slash is also a mandatory to define set. So these, like whatever available in red, these two slash and semicolon is basically your part of the syntax, and index is again a user defined index. So like, there are multiple ways I can define it. So let's say if I am defining like this set I, so I is the name of set, then the description is some canning plants, and then these in, like slash, I have defined the index are the basically members of the set. So Seattle and San Diego is the member. So either you can provide like this. Let's say J is another set, and the like description is that these are the markets, and those markets are at, like New York, Chicago, and Topeka. So these are the different sets and their members. You can define them like all together separately, that is also perfectly fine. Sometimes we can define, like time, we define like set t is like for time, and then 1 to 24. So 1 star 24 is, it's not 1 multiplied 24, it is basically set which have elements like 1, 2, 3, 4, and up to 24. So total 24 number of basically time stamps are there. Sometimes instead of giving a integer number, we can define the same set with some character 1, and then same character and some number. So it will be basically like m1, m2, m3, m at 24. So this is also like, this is how we can also define. If you define it like 1991 to 2004, then it will be basically 1991, 92, 93, and so on. So like different years can be there. uh, Sometimes we define like the set, the name is month, description is month, and it can be month as well. And then I have defined Jan, Feb, March, and June. So these are my different set members. You can see here like it need not to be continuous. It's a user input, so I can define any members in this particular one. Uh, then let's say we were discussing the generator problem, so we can define set G generators and G1 to G5. So this is how we can also define. So there are multiple ways of defining set. uh, Usually, like sometimes we write for summation t time 1 to 24, so we define something like this. Sometimes we define that time is like t1, t2, t3, so instead of m, I could have written t1 and t2 and 24. Okay, so the way we write the program are basically like the index in our notebook, we can define it here in the games programming as well. This one special command is alias. Alias basically creates a copy of the set. Okay, so alias t comma tp is basically it is creating a new copy tp and of the t set. So this is what it is basically. So alias is basically creating one more copy of the same set. Then next is data entry. So data entries, as we discussed earlier, that they are of three type. One is scalar, list or parameters, and then tables. Okay. So for scalars, it's basically single entry. So the syntax is like this. In the red, we have written like scalar. So this is game syntax. Then backslash and colon is also a syntax. Apart from that, this scalar name, so we can provide any name to our scalar. So this is a user defined input. Description, we can provide any description it, and then what will be the value of a particular scalar. So here, like it has been defined like scalar, and then so this is the syntax. Then this is my scalar name, and then this is the description. So price in rupees per unit is the description of this particular scalar, and the price is 5. So this is the value of price. So I can say like if price is value, so this is what we are writing, that price is equals to 5. Okay, so if we have to define lot of scalars, we can define all of them together. This is a mandatory, this is not. So like description, even if you do not provide a description, that is also fine. So description is basically your optional. Okay, name, obviously if we are putting a scalar, it should have certain name, so this is mandatory, and we have to provide some value as well. So this value is also mandatory part. This particular example, we have defined a scalar a. So a is it means a equals to 3, f equals to 7, and then we have defined a scalar d, and then we define like no none values assigned to it. Then we have used a assignment basically instruction, that d is equals to a into f. The d will become 21. So this is also how we can define certain scalars. Okay, so this is the way we can define scalars, either at one at a time or all of them all together. Description is not needed; it's optional. Usually, we provide a description so that whenever we are writing a code, and let's say if we forget about it and come back to that particular code after some time, we should be able to understand the piece of the code. Then parameters are nothing but a matrix, or I will not say matrix, it is a vector. So it can be a row vector or column vector. So like data which is in a vector is defined by the syntax parameter. So this red part is my syntax. So parameter, then parameter name is again user defined input. And if I'm talking about a vector, then it will have a certain length for that particular vector. So that length will be defined by the set or index. Okay, so this has to be provided. Then description is again optional. So this is like optional, I would say. Then in backslash, we have to provide a for which index, what is the value, for another index, what is the value. So we have to provide like with each and every index, what will be the values. So earlier we defined a set, this one, so that we defined a set month and the members was Jan, Feb, March and June. So let's provide some demand to these basically members. So this is my syntax. This is the parameter name and this is our index. So this set we have defined earlier, so we will use it. This is optional, but the description part, so it is optional. Then in backslash I have provided a set member, so it was Jan, Feb, March and June. And then the values with respect to these members is 300, 150 and 2000. Okay, so these are the values available to this particular set. So basically we can say like D is equals to, like from the MATLAB I can say it is 100, 50 and 2000. Okay, so D has these values. And this first set represents January, second is Feb, third is March and fourth is June. So this is how we define our parameters. Once the data is not a single value, it is not a one-dimensional matrix or a vector. Sometimes data is a two-dimensional matrix, or generally we call them tables. So tables is basically the third kind of data entry in the game. So these are the only three ways by which we can enter the data. This data is basically like either we can load from the Excel file, but still the definition are basically like scalar, parameters and tables. So these are the three types of data entries. If you see the syntax for the data entry as well, it's a table is like this is how we are basically making a table. That table name is a user input. Then each table has two dimension, row dimension and column dimension. So this is index I and index j. So we are basically going with the row index and column index. Description is again like optional. And then we have to look for the provide the values. So it is basically index I is moving in this direction, index j is moving in this direction, and we are getting a this particular table. Okay, so different values are available here. So you can see table dij is defined as a name, and I is our first index, j is our second index, and these index were defined like this, like Seattle and San Diego, New York, Chicago and Topeka. So these are like set I and j we earlier defined. So we can define is like d, I and j, and then this is nothing but the description, thousands of miles. Okay, then I moves here, so it is Seattle and Diego, and J moves in this particular direction, which is New York, Chicago, and Topeka. And let's say these are the distance between these cities. Okay, so in miles, this is how we define the table. So two-dimensional data entries. Then by mentioning or like with this particular example we have discussed that the data entities are only two dimensional, but tables basically or the matrices can be of more dimensional. So we can provide a high dimension as well, like three dimensional is also available, four dimensions are also available. But what happens that it is very difficult to visualize those matrices and provide the data accordingly. So what I prefer is only two-dimensional matrix as the input in the form of table, and at max three dimensionals. Higher dimensionals are not advised because sometimes like the if you are writing a code and if you are trying to solve with the help of games, you yourself will get confused. So that's why two dimensionals are fine, three dimensionals are also fine. And if you are good with the tables and like properly labeling them, you can go with the high dimensional as well. Okay, so these are the another examples. So like if you look at this first table, it is basically table name, and gen data is the name of the table, and the one index is generator number, and then other index is kept star as well. Like we don't know what will be those index, so we are keeping them as a star. And the description is generator unit characteristics. So these are the gen number members basically. So like Alta, Park City, and these are the basically different generator bus numbers. And then we are providing these three data with respect to each generator. So like the post function B is 14, 15, 30, 40, and 0. Minimum is 0 and maximum is 40, 170, 520, and so on, which is I think our PGM fiber system. Okay. Sometimes we can define like that this set generator number is already defined with these cities. We can define a set characteristics. So instead of characteristics, I have like you can either type char, or you can use like entire word characteristics, and b, pmin, pmax are the characteristics of that particular generator. So those, based upon those, we can provide a generator table. Okay, generator data for in from the table. uh, Branch data is basically between two nodes, so we can define a set bus. So it is like a set bus, and then we will create a alias of bus comma node. Okay, so now node is also the same bus set, and then we are basically dividing the bus and branch and certain information. Okay, so basically the we are calculating that is three-dimensional matrix. So earlier, like it was two-dimensional matrix. One part is here, one part is here. Now two dimensions are on this particular axis, and third dimension is on this particular axis. Okay, so this is how we can create a three-dimensional matrix where a connection between bus and node has this much x and this much power flow limit. So this is how we can provide a three-dimensional matrix as well. Okay. If you have any doubts in the notation and all, we can discuss about it. The next part is variable. So it's basically this is syntax part, and then variable name with particular indexes is basically the user input, and the description is also optional user input. So like we have defined certain variables where x, ij, x is this part is a description. That's it. So it is variable, so we don't have to provide any value to these variables. Then similarly, if I look at like m variable, and the description is expected value and anything else. So different variables has been defined. Now there is a type of variables basically. So as we discussed, like based upon variable type, we can classify the our optimization in different categories. So in the game support the following like the variables which are visible on your screen as a different types. So free variables are basically continuous variables which can have positive and negative value. Positive variables are only positive, negative variables are only negative, so they cannot have positive. Binary variables can have only 0 and 1, and integer variables can have only 0, 1, 2, 3, and no fractional part in it. So these are the different types of variables which we can define. Okay, so how we can define it? So the initial, like if you define certain variables like x and m has been defined, the by default definition is free variable. So x will also be free, m will also be free. Then we have to mention whether they are positive, negative, binary, or integer variables. So this is how we can define it, like positive variables x. So it means now x will only be positive variable. It is no longer free. So first of all, we define all of them, these variables as a free variables, and then we can define as a like either positive or negative. And you can also directly define x as a positive variable as well. Then the another is equation. So as we looked at the games program as well, sorry, ACOPF program, I have clearly asked you like what are the different variables, what are the different parameters, and how the function is looking like, and what are the constants and everything. So this is why I was asking you multiple times that if we know all the variables, those variables will be defined before. Okay, so we will define those variables, all the parameters. So you have to make sure that what will be the input of those parameters, so that can be defined with the either scalar, table, and list, which is parameters. Okay, and sets are basically like how many sets are there. So based upon that, we can define it. Now equations are have two segments. So far, like everything was declared and defined all together. So like variables were defined and declared together. The data inputs are also defined and declared at the same time. The equations has to be declared first and then defined as well. So the equation declaration is very simple. We will use a command equation, and then user defined a name for that equation, and what are the different index for which we have to write down this particular equation. And description is again optional, you either provide it or not. So we will define multiple equations. Let's say one is cost equation, another is supply equation, another is a demand equation, and their description is define the objective function. It observes the supply limit at a plant, and this define satisfy the demand at the market. So okay, so these are the different equations. Then how we can define basically use different equations. So if I also explained you that this description is optional. Okay, so this is optional. So either I can define it or not. So you can see here what I'm doing is I have defined the equation 1, 2, and 3, or I can like with the set as well, like equation 1, 2, and equation 3, which is which have to be written down for I. Okay, I can be some set. So once we have defined or declared the equation, we will provide the assignment, and the assignment is like eq1 dot dot. So equation 1 and dot dot. This is the syntax basically. So EQ is not syntax, but this double dot means you are going to perform a assignment operation. So double dot, then x plus y is equals to 1. So this equals to is written like is equals to. So this is the difference in standard equals to and your games equals to. Okay, so the equals to is written down like this: equals to. Uh, Less than equals to is written down, I think, L EQ, and greater than equals to is basically equals to G equals to. Okay, so less than equals to is basically equals to L is less than equals to, G is basically equals to greater than and equals to particular value. So this is how we can define the, or basically assign the equations the values. Okay, once we have defined the sets, first of all we will define the set. Based upon set we will provide some input. Okay, so these are the input. Then we will define certain variables, and once we have defined all of these, we will write down the equations basically. So equation 1, 2, and let's say 4, 3, 4. Then the next part is modeling and solving. So modeling is I can model it for only this set of equations. So with this set of equation, I can create a one model, or I can use all of them and create another model, or I can use like any other two and create a particular model. Once a model has been created, we just type solve, and it will give you or solve the entire optimization. This is it. You don't have to worry about like any logic and at all. You just simply have to write down the equation. So it's like generally this is the syntax. So it's basically like model is hard word, transport is whatever the in the name you have provided to the model. So this is a user input, and backslash and semicolon is user input. Here basically you can define the or basically provide the equations. So either you can provide all equations. So if you are written down, let's say 10 equations, and you want to solve a transport problem with considering the equations, then I will use this particular basically model declaration or definition. Then sometimes we don't not use all the equations. So let's say if I use equation 1 and equation 2, so instead of this all I will simply put equation 1 comma equation 2. Okay, so this is also can be done. And then the syntax is like solve the same which same this particular model using with the help of this LP. So it can be LP, MILP, NLP, quadratic programming, QP, and so on. So these basically uh, is basically like which type of problem it is. Then whether you want to minimize or maximize, so you can put either minimizing or maximizing, and which variable you want to minimize or maximize. Okay, so these are basically your solution procedures: LP, NLP, MIP, MINLP, etc. And then either you are going to minimize the, maximize the. So what will be the objective? Okay. Then after this particular statement, uh, games will give you the results. This is it. Okay. Then we can also use a display command that once we have solved this one, just show me x values and eq1 values, and I can use this command. Here dot l is basically level of a particular variable. So at what level or what is the value of a variable? So x dot l is basically uh, I can also say this is value of x, and I would say star because we are solving it after the optimization. If I'm writing down x dot m, it means the dual of x. So what is the value of dual variable of x? Are the lambda and mu we discussed. Similarly, in this particular one, dot m is basically represents marginal value. Okay, xl is lower value, xm is marginal value, and marginal value is basically the dual variable. Uh, we had one example here. So this example is, you can say, it's a economic load dispatch. In economic load dispatch, we have a fixed demand and certain generators who has certain cost function. Uh, this example is kind of economic load dispatch, and generally we call it market clearing. Okay, so this example is market clear example. Here, some generators are there and they are ready to for 100 megawatt, and then they have different prices. That fourth generator is can supply the 100 megawatt at the price of $40 per megawatt hour. Okay, then instead of fixed demand of, like, let's say if I add these up, it's a 300, 400, 500 megawatts. So instead of fixed demand of 500 megawatt, that these demands have certain utility function as well, and based upon that utility function, the buyer one is ready to pay 60 megawatt, and then 35, 25, and 15. So these are, like, different, like, what is that they are willing to pay for consuming certain quantities which are mentioned before. Okay, 150 megawatt or 100 megawatt and so on. So how we can solve it? Mm, okay. So in this particular problem, so we had a question like, some generators are there and they are 100 megawatt. They are offering, generator one is offering 100 megawatt at the rate 10, 20, 30, and 40. So that is at the rate of 10. Generator 2 is offering same megawatt at the rate of 20. Third is at the rate of 30, and fourth is at the rate of 40 megawatt. So generally in market clearing, what we do is we create a supply curve. So I will settle down that this 100 megawatt can be supplied with the price of 10. Then the remaining 100 can be supplied with the price of 20. Okay, and basically we can keep on stacking these with respect to the different number of prices. Okay, and this price will be 40. If you look at another data, which is like, some 150 megawatt at the rate of 60, and 150 at the rate of 35. So these we will basically arrange in the descending order. So first is 150 megawatt at the 60. So 60 will be somewhat here, but that is 150 megawatt. Okay, so 150 megawatt is basically mid of this particular line. So this is starting from 65. Then we have a 100 megawatt at 35. So 100 megawatt at 35. So the third generator was of 30. So this was 30. So it is 35, and that is 100. So it is goes up to this particular part. Okay. Okay. 35. So it will come bit below. Then we have a 25, 150. So 150, and then we have 115. So 15, and then 100 megawatt. So this is our market clearing algorithm where the quantity which can be cleared is this much. So it is 100, uh, 250, and the price will be the 30. Let's see how we can model this particular problem. So it's basically maximization of this area. First of all, how we can get this particular area. So if I go from top and remove this below area bar, then I can easily get it. So it is nothing but the total area is basically 65 into 65 into, so this is the 65 into 150 and then 35 into remaining 100. So that is 65 into P1 plus 35 into P2, and actually demand. So P1D and P2D plus I will remove this particular area, so I will get this particular area in between. So it is basically the minus of 10 into PG1 minus plus 20 into PG3 plus 30 into PG3, and this will be 2. Right? Just a second. Okay. This is how it will look like, and let's see if you are able to make it like this. So in games program, if I have written down, so I have provided certain scalars. Okay, so one scalar is C1. Okay, and C1 is the supply bid price of generator 1, and I have defined it 10. Okay, so this is what I have defined. As I explained you that this description is uh, options, whether you can provide it or not. So you can see from here that the very first scalar I have defined a certain description, but second one I have just written down some gibberish, and the third scalar and onwards I have not provided any description. Okay, so we can say that, like, the cost functions for the generator which at which it is going to produce is 10, 20, 30, and 40. So C4 up to C4 is these values. Then we can define the cost at which the demand is willing to purchase. So it is A1, A2, A3, and A4. So that is 60, 35, 25, and 15. Okay. Then I will define a variable which is obj or objective. So that variable I have defined, and then I have defined some positive variables that all of the P1, P2, P3, P4. So these are like power generation, and D1, D2, D3, D4 are power demand. I have defined positive variables that these should be positive. Then certain upper bound has been defined that P1, P2, P3 can have demand of 100, and that is basically available here that they can provide 100. Another was is 150 and 100. So you can see that D1 up is 150, D2 up is 100, and then D3 up is 150, and D4 up is 100. Okay. Now let's define the variable. So you can see I have defined only one variable, and then I have defined certain like P1, in total 8 variables as a positive variables. You can also define these variables like P1, P2, P3 in with respect to above variable here with a comma, and then you can define them positive there. Okay, these are positive as well. So that is also perfectly fine. Now I have provided a equation declaration. So this is like I am providing that I'm going to have two equations, and the description part is still like option. So I am not providing any description with these two equations. So I have two equations. One is objective fund and another is power balance. So I have defined power balance that it should be P1 plus P2 plus P3 plus P4 should be equals to D1, D2, D3, D4. So that is what we have written here, like one equation. Another is objective function is equals to C1 P1 plus C2 P2 and so on. And then we are basically writing down is like market. Okay, and then whatever is the second command is, it's a user input, so you can put it anything, market clearing, your name, you can put my name, whatever. So that is your market clearing. And then I am defining all the equations that, like I have only two equations, so all the equations should be optimized. Okay, then I'm using a condition solve my model, which has I am given a name market clearing using linear programming. So the method is also provided that it should be linear programming. Then we have to minimize. So either you can write down like full minimizing or maximizing, or you can simply write down min or max as well. That is also fine. And then obj. So once you run it, you can see that the some normal completion has been done and some values of P1, P2, P3 will come. So like here you can see that P1 value is 100, P2 is 100 and P3 is 50. The total demand is 100, like to the total demand which is being supplied by this generator is roughly around like 100 megawatts from the generator 1, 100 from generator 2 and 50 is from generator 3. So total of 250 megawatt is being supplied, and the loads are again same 150 and 100, and you can see that from this particular example as well. So like 150 and 100 they are cleared, 100 and 50 of the third generator has been cleared. So those are also available in the solution, like 100, 150, 150 and 100. Okay, so if you read the model statistic, we will talk about it. First, let's see the economic load dispatch problem. So this is our economic load dispatch problem, and this is how I write it. Okay, minimization of P total cost equals to summation over 1 to n CIPI subject to the power balance equation and power generation limits. So how can we write that in a code? So you can see, let's say these are my codes. So the very first thing which we are going to define in games is sets. Here I have defined uh, set I. Okay, so set I is basically, this is name of the set. So I have given a name I to the set, and the description is generators. So that these I's are generators. That's it. Then P1, P2, P3, P4 are let's say 4 generators available to us. Okay, so P1 to P4 are the generators. Okay, then we can define that. Okay, there are some characteristics. So generator character is basically generator characteristics we have defined. So these are basically the description is generator characteristics, and any generator economic load dispatch problem we have discussed multiple times with the like concept building, and then the demo with the help of sorry MATLAB as well, that these can be defined. And we have, excuse me. Okay, so a generator will have some certain cost functions. So those are A, B, and C. So like the different cost functions are there, and then some upper limit and lower limit. So these are the set I have defined. The same name. It's you don't have to provide anything else. Or here in like instead of up limb, you can put, let's say, min or up. So max and min generally we avoid here. Generally we provide like max for the generator maximum limit and min for the generator minimum limit. But I would not recommend using max and min, because we use that for our last uh, parameter, like we are trying to solve this either minimizing and maximizing, so those are also max and min, so I would not prefer. So that's why upper limit and lower limit I have used. You can write the entire word as well, like lower limit without space. Okay, just make sure that. Then some CG is subset of this generator characteristics, and we have defined that these are also ABC. And by putting this gen characteristic here is defining a subset, and these ABCs are same as well. So this is how we define it. Then we have defined a alias that I is also J. Both are same. Now, once set has been defined, we will give the input, basically different input data. You can see the generator cost characteristics and limits. So let's say the P1, P2, P3 are the three generators, and then A, B, and C are given like this. Okay, so this is what let's say is given. And you can see here value of A is 0. So this is not a second order cost function, it is a linear cost function. Only B component is given as a 10, 20, and 10.833. So this is like the data we have. Then upper limit is there, which is 100 for each, and the 180 for the third generator, and some lower limit of 0, 37.5, and 45 megawatts. Then here is basically different exponents of the cost function. So like this A is like power P power 0, B is with the P power 1, and C is with the P power 2. So the C coefficient is the second order for this particular code, and A's coefficient is basically the constant one. These are the power parameter we have defined. Then we have discussed like the loss economic load dispatch problem with the losses as an integral part of it. So let's say some B coefficient or B matrix is defined as well. So it's table Bij. So I set of generators, and J is a copy of I. So it is also the same. So P1, P2, P3 is there. P1, P2, P3 is on this side. And then these are the different B coefficients with respect to these terms. So if you remember, the B coefficients were defined after this part. Yes. So the B coefficient has three components. One is 0, 0, one is I0, and Ij. Okay, so Ij is basically second order, I naught is basically individual or linear, and B naught is the constant. So same thing has been defined here, that this Bij is with like when both the two parties square terms are there, then this B naught is basically the linear cost loss coefficient. So these are with respect to P1, P2, P3, and some B initial B naught is the constant loss coefficient. So that is also provided here. Then total demand is given is like let's say 210. So these are the input parameters which we have, and we have provided that here. After that, we will simply write down the variables. So variables I have defined like the cost. Okay, so you can see here as well. So in the formulation, you can see that we have defined cost is equals to this value. So cost is also defined as a variable, that okay, it will depend upon the variable. So this cost will also be going to vary with respect to the our decision variables. Losses will also vary with respect to our decision variables, and P is obviously power generation. So that is also variable. So these three variables are defined, and out of which P is defined as a positive variable. That is perfectly fine. Now I can define upper value for each and every generator like this, that like the variable P put up is basically upper value. Dot low is our lower limit. So this is how, like with up and low. So this dot up and dot low are also syntax in the games. Okay. Then ith generator, we can provide this entire matrix of upper limit as a upper limit of these variables, and lower limit is as a lower limit for the variable p, and this will come from the this particular table gen data and this column respective. So columns are basically upper limit or lower limit. Here I don't have to remember whether it is like fourth column and fifth column, and earlier we had this mat power input case file where the maximum minimum was available at column number 9 and 10. Okay, so how we can assign it? I can directly say that generator data for all I, and whatever is the member up limit, provide that value. Okay, so whatever I have given the number. So here in games, in MATLAB, all the indexing is like 1 2 3 4 5 only, in any table or in any variable as well. Here in MATLAB, the indexing can be anything. So here, like instead of 1 2 3, I'm putting up limit. Up limit is my index. Okay. Then similarly, like roll data is defined. Then here I have defined certain equations, and one extra equation basically. So you can see the very first is cos is equals to. So with this particular function, okay, so this was the earlier we have defined, and then if I say, okay, so here you can see like the very first equation which I have defined was post function. So in MATLAB, basically games code, we have to write it like this. So this is a user defined name, post function, post fn. Then double dot is the syntax that, okay, if we are writing double dot in front of equation, which means we are defining this equation. So it is written cost. So I have mentioned cost. So it is cost equals to. So it is equals to. So this is how we write down equals to in MATLAB. So you can see it now, right? So it is equals to. Then we have a summation over n. So instead of over n, we are providing a summation over I, and G. G is basically the coefficient power. Okay. So, so the same formulation, like this particular part, if CI PI is like AI PI square plus BI PI plus CI PI. We can what we are writing is basically the same term can be written down like this: summation over I equals to 1 to n, and then summation over, let's say, some power equals to 0 to 2. Okay, and some coefficient. Okay, and so some coefficient p, and whatever pgi, that power p, and then respectively I is also placed. What we are doing is, let's say for a generator number 1, it will be a1 and p naught, then Pg1 and power is 0 plus generator number 1 uh, P1 and then Pg1 and power is 1 plus how emission constants can be included in economic load dispatch. Very easily, we will discuss about it. Okay, so 1 and 2 Pg1, that is, and power 2. So you can see this term will become power 1 will become 1. So this is nothing but the constant part. So we are writing like this, AP square plus BP plus C. So this is nothing but the C. This is BP. This is P square. So this is how we can also write down with the double sum. So the same thing is been provided here. It's basically summation over I, summation over G. Generator data. So whatever is our generator data, and power is our PI, and that I will come from the the exponential terms which we have defined earlier, which was 0, 1, and 2. So you can see like the exponential terms was defined 0, 1, and 2. So we are basically using this particular function. So this gives you the cost function. Okay. There is a question how emission constants can be included in the economic load dispatch. So emissions are basically have certain function as well. So this emission, usually we keep or put that emission with respect to basically in the objective function. And what happens that if we like those that is also assumed as a second order utility function, emission function, not utility, I would say. So some emission function is also considered as a second order function with some negative sign and different values. And as power is being basically produced, that emission it will create some emission as well. So if we are trying to minimize the cost, we can also add that emission as a objective and try to minimize emission as well with the economic load dispatch. The equation will remain same. Even though we are trying to minimize the emission, our objective is to that total generation should be equals to the power demand, and our generation should be within the maximum and minimum limit. So this is how we can include emission as well in the objective function. Usually the emission and the cost are conflicting objectives, so we can define that uh, there is a question, can B note in loss coefficient can be considered as emission? So B note was basically the function of losses and double summation of BII, PI, PJ, then single summation of BI note, PI plus B note. So this was the loss function, and this loss function will go in the power balance equation. And that was like summation of power produced should be equal to the power demand plus power losses. Okay, so this is just losses. Even if I look at this particular one, let's say all the power productions are 0. So all the like PI and PJ, if they are 0, there are still some loss. Okay, so this is the meaning of B note, and we can assume that because of the shunt devices in the system, some active or reactive, some power flows will be there, and those like losses caused by those shunt devices which are not power injections is basically B not, and it can never be used as an like emission coefficient. Emissions usually go with the objective function. Okay, so okay, while solving genetic algorithm, I will consider the example of economic load dispatch with emission. Okay, so in that example, we will try to cover the emissions as well. Okay, so we were looking at this particular formulation, and so you can see here the losses has been identified, defined the same way which I have written below, that the losses are equals to. So you can see here that losses are equals to losses equals to B naught plus summation of over I B naught I into Pi. Very simple. Okay. Then summation over Ij, and then Pi Bij Pj. The same way which I have written here, that this is the losses, like summation over I, summation over j, and Bij Pi Pj. Okay. So this is what I have written, like Pi and Pj, and then summation over I B I naught Pi. So the same way I have written here. So that's why that this writing the formulation or mathematics in this particular like tool, which is games, is very easy, because we write it exactly the same way. Okay, then this and another constant is basically our power balance constant. So it is like demand plus losses is equals to summation of Pi. That's it. That demand plus losses should be equals to summation of power generation. So this is how I am writing it here. And the same way I have been writing the power balance equation. Okay. So this is how I was writing. Right. Okay. It has been moved. The power balance equation was summation of Pi equals to PD plus T loss. This was the equation, and we are also writing it like this, that the demand plus losses is equals to summation over I plus PG. I have defined one more equation, and which says that losses are equals to 0. Okay, so this extra equation, which is in line number 52, I have defined it additionally. So let's say if I use this particular equation, then losses are 0, and if this in line number 51, if this losses is equals to 0, then the economic loss dispatch problem will become ELD without losses. And if I do not consider the line number 52, then my economic load dispatch problem with losses will be there. So in the same model, I have defined all the equations, and let's say I am trying to solve this particular one. So first of all, I have to define the model. So this is the syntax model. Then I have defined that economic load dispatch without loss. Very simple. So like, I have defined it that this is the name I'm providing. You can provide it anything. Then I am trying to uh, model the equations. So I have given the equations, and equations are, one is cost function, another is demand constant, and the third one is the loss function note. So the cost function is our standard cost function, AP square plus BP plus C. So summation over that. So that is defined in the cost function. Demand constant is our this part here. Losses is also defined, but with loss function 0, I am defining it that these losses are 0. And I'm not utilizing this particular constant, which is at line number 50 in this model. So I have defined a model where losses are actually not present. Then if with losses I have to define, I will use the same constant, and instead of like loss function 0, I have defined some loss function. So losses, which is also variable, is given by this particular equation, and that will be used in demand constant. So I have defined upper 3. Now I can solve these. So one is, so in the same formulation, I have defined two types at the same time, without loss and with loss. Then I can solve the same problem, either minimizing the cost or basically minimizing the network losses as well. Okay. And if I could have defined emission as well, I can basically minimize emissions as well. Like, somebody asked me, like, how can we put the emission? So you just have to define a equation here. Okay, let's say emission, emission function. Okay, and then you can define. So once emission equation is defined, I will define the same emission dot dot, and I will define, like, some emissions are equals to, then I have to put whatever is the function I have. Usually for that I need the coefficients of the emission function, and so far, like, I don't have the data with me, otherwise I could have placed it here. So let's say define it 0 initially. Okay. Otherwise, you can just like the cost function. Usually, the cost function and emission functions looks like similar with some positive and negative terminologies. So, just like cost function, you can define the emission function. So it's like, instead of here 0, you can define it that as well. And then without losses, you can define it. With losses, you can define it. And sorry. Then so, we are basically here solving the ELD without losses problem, and then we are minimizing the cost. So cost is a variable, and I'm trying to minimizing it. So you can see this is here, like, I'm defined that. So I have placed this minimization over total cost equals to this. So this cost function I'm minimizing. So this is what I'm doing. So the exactly same way I have written that minimize the cost and using NLP. So it's basically quadratic problem and it's a non-linear in the nature. So that's why using non-linear programming. Then the second time is, like, I'm also solving the same formulation EDC with loss. So I have defined that EDC with loss will have a loss function and minimizing the cost again. And then we are solving the EDC with loss, but this time we are minimizing the losses. So you can see here, like, the first thing is without loss at 63, and 65, 66 lines have basically the with loss modeling, but different objectives, either minimizing the cost or minimizing the losses. Let's solve it. So if I run it, some error is coming, and it is coming because I have defined 4 generators, and in this set I basically provided only 3. So okay, floating entry ignored. Why? Okay, so here some error is coming, and it is because I have defined the equation, but I have not defined emission as a variable, because there is no variable name emission. So that's why some error is coming. So you can define emission as a variable, so that, like, for the time being I'm deleting it. and let's run it. So yes, normally it has been completed. I will click here, and some data is available, and let's see how it looks like. So first of all, it has been given this information. I think you can see it. So this is what it is given. So whatever we have written, it will provide as it is. First of all, so this is the program we have written. So it will consider everything, like these two lines I have commented earlier. So that is also provided, and then we have solved it. Then some information will come, and it says that the compilation time is almost 0 seconds. Some information about the solver, and like this information, like message from the games. Then whatever we have defined, the different equations, it will uh, write you down that how it understand and how it interpret those equations. So the cost function equation, it will write is like minus 10 into P1 minus 20 into P2 minus 10.33. So these were the objectives into P3 plus cost equals to 0. So it means cost is equals to summation of these three objective functions. So it is like B1 P1 plus B2 P2 plus B3 P3, because we don't have A and C. And some information is provided here, like let's not go into that. Then the second constraint was demand, and it was written that it's a minus P1 minus P2 minus P3 plus losses is equals to 210. So this was the demand given to us, and we defined earlier the loss function was that 0. So loss function is equals to losses are 0. So this is we have defined earlier as well, and it is given that loss is equals to 0. So this is the simply it will understand that the variable is 0. Then some message is there. uh, then some, like how the different variables and input data is provided. So what are like P1. So P1 will have like provided in the cost function, and the different constants, and what will be the different values. So it has been provided here. So this is like all the like how the MATLAB is, sorry, games is like understanding it. Then some model information, like how blocks, the three blocks of equations was there. Single equations were 3, single variables were 5, block of variables was only 3. So the only three variables were block of variables was 3, but actual variables were 5. So you can see here, like the variables we have defined at 3 only, where cost is one variable, loss is one variable, P is one block of variable, and set I represents three generators. So it is actually three variables. So 3 plus 2, 5. Our block of variable is only 3. This is what here it is defined. What are the non-zero elements and non-linear elements, and code length, constant pool, and everything is provided here. Then it is providing some solving summary, that this is the name of the model which we have provided. The objective was to like whatever we have given it, the direction was to minimize, and it is available in 63 number line. Type was NLP, and then the games used a Conopt solver. So there are many solver, and games used Conopt to solve the nonlinear programming. The solver status was normal completion, so it means we have obtained a good optimal output. Okay, and model status is locally optimal. So for on non-linear problems, it's very difficult to claim that global optimal has been obtained. So usually the status is local optimal, and then how many resources has been used and everything. So it is sold with a demo license. No commercial use can be done with this particular one, and then some function values has been provided, variable values. So what I will do is I will directly go to the variables. Okay, so here is the variables. You can see that the P1 value is 100, P2 is 37, and then 72. Okay, and then we have like loss variable and cost variable. So these losses are 0 and cost is 2500 and something. Then if I look at the equations, I have a cost function equation, I have a power balance equation and loss function. This power balance equation has a marginal value of 10.833. So that is basically you can say the system price. Okay, and then so this is the output. Now if we see the second model was our basically here is the different functions, and you can see the marginal value has been increased because of the losses. So losses in affects the marginal value. Okay, and then you can also see like different variables. So p values are affected. So let's write them down. So if I look at the marginal value of this one, so we have considering basically three cases. So in economic load dispatch, case one was basically and then uh, with minimization of cost, and then with losses and minimization of loss. So with losses, you can see the margin value was 10.833. Okay, wait. 10.833. So I will put 10.833 was the lambda. Okay, and then P1, P2, and P3. Let's say what will be the different values of power generation. So the P1, P2, P3 is here. It's 137.5. So it is 137.5 and then 72.5. So these are the power generations. Then if we look at the second part, the lambda is 11.41. So it's 11.4 something. P1 is, you can see, look at here, like that values. So this is lower limit. This is actual value of P1, P2 and P3. So these are like P1, P2, P3. These are the upper limit, and the marginal values are basically the constant, are basically the whenever the value hits to a limit, it creates a produce a marginal value. This I think we have discussed a lot as well. So as this is the lower limit, the level was also the same. That's why we are getting a marginal value in the same MATLAB as well. We discussed that whenever uh, a variable hits to a limit, either maximum or minimum, it will marginal value will have a certain significant, otherwise it will be very minimum. So it is that 10 to power minus 10, because it is within the bounds. This one also is within the bounds, like upper is 100, lower is 0. So the marginal value is here 0. Both represents 0 in gains, for your knowledge. Okay, so it's 92, 37 and 88.9. So it's roughly around 97, 37.5 and like 88.9 and something, some values are here. And if I look at the with losses, so the last one is basically solve equation and demand function. Some lambda is coming here, and it is coming equals to 0.07. So let me put it 0.0784, and then some p is there, which is 58.1, 58.1, then 38 point something, and then 121.69. So what is the significance of this information here? So if I goes here as well, like we are trying to do minimization of the cost. So this lambda is this much, then lambda has been increased, and then lambda is very low. So why the lambda value is very low? Can anyone explain me, like so far I think I have explained you many times this lambda has certain significance, and from that concept maybe you can explain that why this the third case lambda is very low. Anyone? I hope you are typing your response. So I will move to the P1, P2, P3, then I will come back to the lambda again. Okay. So you can see when there was no losses, when we are minimizing the cost, this was the schedule. Okay, so 137.5 and 72.5, perfectly fine. Then when we are using the same objective function, minimization of the cost, and we are trying to solve minimization of the losses, the this has been reduced. It is almost equal because it is on the minimum limit, and this has been increased. Why it is happening? That it means that P1 is creating more losses and P3 is creating less losses. So let's see if we can make this thing out of the data. I don't know whether we will be able to see it, because sometimes yes. So we have to look at the P1 and P3. So P1 is creating the losses of 0.06, and P3 is creating, like P3 by P3 is 0.2 or zero point 0.3. So it is 0.6 and it is roughly around 0. Sorry, 0.06 and it is 0.03. So half losses are being created by the third generator as compared to the first one. If I just look at the one element, now with respect to 1 and 2 and 3 and 2 is almost same, like 0.009, 0.009. And then yeah, so, so with respect to 2, 1 and 3 are almost same. Obviously, they will be the same. So the individual, like P33 and P11, they are basically half as compared to the first generator. So the first generator is creating more losses as compared to the third generator. So whenever we are trying to solve it with the losses into a picture, we want to increase this generator more, because it creating less losses, and if less losses are there, less has to be produced, and the overall cost will be less as well. Okay, so that's why we have reduced this one and increased this. Now if I look at the third one, you can see that we have observed that, okay, this is roughly around same 37.5 to 38.5, but from P1 to P3, you can clearly see that the third generator, and we also have seen that the third generator is creating less losses. Okay, and first generator is creating very high losses. So that's why we are set it to a very high value, because losses are very less because of the third generation. So that's why we start increasing this value, and we decrease this particular value because it is creating too much losses. And then the second generator, it was creating a moderate number of losses. So we are not going into that, but I think the cost function is also very high, and it will depend upon the other parameters. So this is okay, but you can see by comparing 1 and 3, we have increased this part and we have decreased it to very low value. As I explained you earlier, in economic load dispatch, the lambda represents the system price, and I think I'm again stating myself that the system price is only when the objective is of minimization of the cost or maximization of the uh, social welfare, or you can also put like profit sometimes if cost is zero. So this is like system price. So if there are no losses, obviously the marginal cost of the producing the demand will be less. If losses are happening, then the cost is going to be increased. So that's why it has been increased from 10.8 to 11.4. With network losses, this lambda now does not represent the uh, incremental prices. It is representing the incremental losses, and that are basically that those will be affected by the loss coefficient and not on the cost coefficients. Like ABC will not affect the lambda. Now this lambda is in terms of B coefficients, and that's why it is coming out very low. Any doubt so far? You can ask me any like if you have any question, you can ask me right now. For this part, I think we have already discussed. Then I will show you quickly, like the DCOPF, so that we will wind up the this particular part. So this is a like some built-in code I have obtained. It is available on the internet as well. You can just simply write down DCOPF GMS code. You will find it. So that 5 bus system we have discussed so far, like case 5. This data is also the same. It is of the case 5 system. Here, some sets has been defined. You can see these are the different sets which has been defined here, and those are basically like a set of bus. So we have 5 buses. So 1, 2, 3, 4, 5 is one defined. We have defined a slack bus, which is a subset of bus, and that is one. That first bus is my slack bus. Then some generator numbers are there, and these numbers are provided like this, like the city's name, or you can provide that with nodes as well, like at one, then at one, then 3, 4, and 5 are basically the generator numbers. One scalar is defined, and that is basically the power base, and the base MVA is 100. Okay, and we have defined that buses are equals to the nodes as well, like the same asset has been defined, copied. Then we have provided some generator data. So generator data is basically like these cities have uh, 5 generators, and 5 generators have the cost coefficients, linear cost coefficients of 14, 15, 30, 40, and 10, P min of 0, and P max of certain values. Uh, then some connectivity is defined. So like which generator is connected at what bus. So this has been defined by this set. So you can say it is a generator incidence matrix as well, like where is the generator connected. So the generator is defined like with the name of the city. So Alta and Park City are connected at bus number 1. Solitude is connected at 3. Sundance is connected at 4, and Brington is connected at bus number 5. Okay, so this is the information available so far in case 5 as well. Then some bus data is defined, that and it is defined as a demand. So buses and some PD is defined. Okay, so at bus number 2, 3, and 4, certain demand is there. One important thing is like in this particular table we are providing that the index is bus, and bus has 5 index, 1, 2, 3, 4, and 5, but we are not defining anything with bus index 1 and bus index 4. We are not defining it. So it is understood that if we are not defining it, it is will be 0. Okay, so that is very good feature. Like some values are so we do not have to assign them 0. It is by default 0 if you are not providing that information in a particular set. Okay, then some connectivity is defined, that there are connections. So, connections are between 1 and 2, 2 and 3, 3 and 4, 4 and 1, 4 and 5, and 5 and 1. So this is basically line connectivity, and it is defined that this set is basically whenever we these connections are there, the values are will be equals to 1. So like in a set, this particular set we have defined that the values are 1. So it's like the lines are basically connected and the status is 1. So this is how it has been defined. Then next is some parameters. So we have defined these connectivities like 1 2 1 4 and like these the same connectivities. Okay, and we have defined that some x values reactance is these are the reactance, and these are the line flow limits of these branches. So this is also provided in the table, and then it is basically provided that for any this branch x, if the branch data is provided 0, then that x will be considered whatever is the x. If it is 0, we will put that into the x. Okay, so we will use it as it is, like if some information is not provided here for all the like other branch and nodes, that will be 0, and that 0 value will be provided here. So it's basically some conditions are there to make it generalize. Okay, okay, sorry. Now the variables which has been defined is only objective function OF, power flow between I and J, PG generator number, and some delta which is angles. And no declaration or basically description is provided because that is optional. Some equations are defined, and the names were equation 1 2 and 3, and no declaration is also provided here. And okay, so now Pij is basically provided here, and what we are doing is you can see that constant one is basically between four node bus and node. So it is uh, any Pij are basically like for all ij set of L we have to write down. So power flow has to be calculated for a pair of ij in a set of lines. So that is basically the constant will be calculated for a pair of I and j. One thing is provided that dollar is a if condition in our games code. So this dollar is concerned that this has to be written only for the connection which I have provided. Okay, not for all ij. So there will be a lot of combinations, but the connections will be limited. So like like let's say there is no connection between 1 and 6, okay, or 1 and 3. So for that it should not write this particular constant. So whatever the connection I have provided above here in connects, only for those values like 1 to so there is like there is no connection between 1 and 3. So for that it should not write down the Pij. Otherwise if I do not provide this dollar constant, it will try to write down for all combinations. Then we can calculate the Pij. So Pij bus comma node is equals to uh, so it is basically delta bus. So delta I minus delta j divided by xij, and we can also keep it like instead of divided by, we can multiply with the bij. So 1 upon x is equals to bij. So this is how we are writing it down, like Pij was delta 1 minus delta 2 upon xij, and the same thing we are writing here, delta bus minus delta node upon, and instead of writing down multiple times, we are using the set. So delta bus minus delta node. So for all the ij, it will write it down. Okay, then another thing is our another constant, which is basically uh, power balance equation. So you can say like connection at bus. So at every bus we will write down this particular second equation, and here what we are seeing that it is basically some plus symbol, summation of generator number. Okay, so if there are multiple generators at particular bus, it will be defined by gb connect, like for that particular bus how many numbers of generators are connected. So we can see that like in bus number 1 there are two generators. So it will do the summation over those generators, and it is whatever is the PG variable, so it will do the summation. Okay, so PG P1 plus P1 at the bus 1 minus bus data, so whatever is the demand or that particular bus divided by the base. Okay, so we have to convert everything into per unit. Okay, so we have divided it by base equals to summation of Pij. So that is we have already established that Pg minus Pd equals to summation of Pij. So this is what we are writing here: Pg minus Pd equals to summation over all the nodes, and provided that they are part of the connectivity which we have provided, and whatever Pij we have calculated for that, so we will do the summation. Okay, and what then the last one is basically the objective function, and objective function is basically summation over all the generators, so generator numbers, and whatever is the PG power output, and then uh, so we have generator data. So this is our linear cost function. So whatever is the B coefficient, so it is basically P into B into S base. S base is to basically, we are considering everything into per unit. So we have to convert this coefficient B into per unit as well. So that's why this has been multiplied with the S base, and this is my objective function. Okay. So some model has been identified so far. Now, either you can model it, or basically you can this 84 line you can get rid of as well, because it is for load flow so far. So the same code can be used for to like obtain the load flow solution. Then some generator limits has been defined, like PG low equals to like with each respective generator, and from the generator data whatever is the P min, we can use that as a minimum limit divided by S base as well, because to convert it into per unit. Then similarly, and upper limit has been defined, and that is with like for all the generator numbers, and like all the generators, uh, take the data from the generator data and the Pmax data divided by the base value. So this is maximum limit. Delta up is defined like pi. So this is what we have defined in MATLAB as well. Like angle varies from pi to minus pi. So up is pi, lower is minus pi, and then delta is having a fixed value. So this f is important as well. It is another syntax. So dot up is basically creating a upper value. Dot low is creating a lower value on a variables. Fx gives you a fixed value. Okay. So delta is having a fixed value, and for which slack we have defined. So we have defined a slack bus, and that was bus number 1, and we are giving that it should be equals to 0. So this is also defined. Okay. Then one more thing is like the formulation which we have written, we do not use Pij as a variable in this particular one code. Basically we are using excuse me, Pij as a variable, like the variable Pij is defined as a variable, you can see here. So if it is defined as a variable, the line flow constraints which we defined in inequality constraints can go into sorry, limits. Okay, so those can go into the like lower bound and upper bound. So that's why the Pij up for like bus is I and node is, let's say, J. Syntax. A dollar symbol is like it is like if, and that is like for only for the connections which we have provided between the bus and nodes, only for those bus node sorry pairs, we can define the line limit equals to the branch data, and whatever is the limit is provided there divided by the base, like converting it that into per unit as well. And similarly the lower limit can also be provided, but with a minus sign. because the we also use the like maximum limit is pf max and minimum limit was minus pf max, so we are using the same limit with a positive and negative. Then simply if you solve a load flow model, so we have defined all the variables, and if we solve the load flow model and minimizing the objective OF function, which is here in constant 3, and that is our cost. So basically, we are minimizing the cost and using linear programming. It's a DCOPF. Then some report, and these are the something, and like display is also a command to display certain variables. And if we run it, we will basically able to see like what is the output, and let's see that what is in display. So let's see what has been provided in the display. So you can see like the first generator is providing uh, okay, let's look at the variables directly, and let me see the PG. So PG is 0.4, so we also got the 0.4, then 1.7, then 3.23 and 4.66. So these are the variables values which we are getting. And then let me see the solution report as well. So it is also providing that like normal completion is there, and as this is a linear problem, so that's why instead of locally optimal, we are the message was basically the optimal solution has been obtained. So solve variables will give me the value of variable, like what is the objective function value. So this is the objective function value, and then Pij. So different power flows can also be. So Pij was defined as like power flow between I and j. So between 1 and 2, this is the power flow, and these were the limits, like 4. So upper is like 4.0, minus 4.0. So so you can see like all the combination like back and forth has been created. So it is 2.4972, and other way around is minus 2.4972. Okay, so we are looking at both the direction. One thing is this 4-5 line is basically congested, you can see, and this is congested, so it is giving some marginal value as well. Okay, and then if you look at the angles, so these are the angle values. So like pi and minus pi is there, and these values we are getting it. So you can I will share this code with you, and it is also available online. Simply like type DCOPF code games, so you will get it. And it is very fundamental code with a less number of variables, so that's why we are able to solve it with our demo version of the games. If number of constants increase, then it is very difficult to solve with a free demo version. So if you have any doubts, you can ask me. I will share this code, and I recommend, we have written it in MATLAB as well for DCOPF and economic load dispatch. We have written in the games, and compare the results and see like what like how the variables are being defined, if they are giving the same results, what are the value of dual variables, and what are the value of like P1, P2, P3 are like all the generator outputs. If they are different, try to see why they are different. And trust me, there are different values, like whatever the code we have shown, the games code I have shown you for DCOPF and economic load dispatch, and for economic load uh, they may have the different values. They should not, because in the both MATLAB and games we are trying to solve the optimization. So the optimal solution should be the same, but maybe some data is plus or minus. So that's why the values are coming different. So if I do have any doubts, please ask them. I'm happy to answer them. There was one question about a quiz on the WhatsApp group. So let me tell you that quiz will be open for tomorrow, 8 to 8, 8 a.m. to 8 p.m. And so you can attempt it whenever you are free, but the time is only 30 minutes. Okay, to finish the quiz. That's it. Okay, then thank you very much. We will have one day, so tomorrow is Sunday, we will have that break, and then we will resume on, I think, Monday. So that's all from my side. If you have any doubts, feel free to ask. You can put your doubts, you can message me on WhatsApp as well. I will like maybe call you or try to resolve the doubts on the text as well. Thank you.